Shall we start or we'll wait for some time, let the others join?
Good evening, sir.
Yeah, good evening. That will wait for some time, and then others will join, then we can start the session. Uh, till the last week, any doubt is there, or that if you want me to clarify something, I will give the brief till the fourth week, like till the last week. Then we'll go ahead with that regression, and slowly we'll start for the new that the network also. And today we'll touch that back propagation and then forward propagation, that how we are going to find out the cost or that the neural network and all. And the next week we'll be going to start with the CNN, that the convolution neural that the network will be there. Slowly that we are making the base for that machine learning course. Actually, this application part and all that that mostly will go in the next week. Next week, I can say, like we'll solve some problem actually, and we'll take some sort of data, maybe supervised learning. Like we'll start with the CNN itself, and we'll go ahead with that as planned earlier. Like as till this week, we are much into the regression fundamentals. That how that so that the neuron will so that way you work it out. So if we have the idea, then how it went till the last week, like we started with the how that algebra is going to take part, or that how it's going to help it out, like the gradient and then the Jacobian and then the matrices, that the multiplications and all. Then we jump into the probability to deal about the threshold and all, and threshold value, or maybe the joint probability distributions and all, and then the normalizations and all that we have to see around. After that, we went to the optimization. Optimization, that in that what we have done, like mostly we would deal about the minimization. Like that's that we are going to minimize the error. Even though that can be that optimization stand for either it can be maximization or like that the minimization. So a so that the maximum problems can be turned into the minimization problem. So there is a no much issue is there. So in that also, so that came that the what you can say, that's the gradient descent and all, it came around, and we have to get the optimal value for that parameter, that the model will give the better results, either it in terms of accuracy or in terms of the error should be less. So that's how we have deal about that. So for that, that the once we have made all these grounds and all, so then we went to that the linear regression. So I think till the linear regression that we have discussed all around fully. I think we'll wait for 2 more minutes. Then we'll start today. Will be the logistic regression. That will be the classification model. Till now that we have seen that the linear regression, and then we'll see that the classification model, like that's called logistic regression. In that also we'll be having what is the difference, why we are going for the logistic regression, where it's going to use it out. It can be the binary classification, or it can be multinomial classification. Means like that's called that's called classification. And once we'll jump into that, so then we'll see what is the cost function. Because if you see for the linear regression, we have seen list regression, list square that error. But it's the same thing if we talk into logistic regression, it might not get the better results. How we will not get the better result? That so that's also we'll speak about that. To counter that, we so people came like that the scientists came across one functions that we call sigmoid. Sigmoid also, in that sigmoid also we have the binary cross entropy, BCE. So what is that also that we so that we'll also discuss about that, because it's all about the cost function, or if any error is there, so it should be going much more, that cost should be higher, so that so that the model will be going to behave in different way, so that we can make some guesses or do some that the corrections and all. So based upon that, that we'll see around, then we'll introduce that how that the neuron so that's called neural network work. We'll see first the biological neurons and how it's going to make the things out. Then if we are going to deal with the single that the layer, so that's called NN. NN, it's nothing and it's just wait 1 minute. So if we are going to deal with the one layer, so it will call neural tap the network. And if we have the more than one that the hidden layer, that will see what is the hidden layer, what is that layer, and then what is the activator function, and what is sigmoid, what is that linear functions and all that we'll see, will slowly will come across. And we were having some problem to discuss the last class actually. If I'll talk about like based upon that linear that the model, I'll go with the problem and then we'll start with the logistics, that the regression. I'll see around the week 4 content. Uh, just one thing I want, like any doubt or anything that you want me to clarify, or is something like if you have any doubt, so till this week, like till the fourth week, what we have discussed and all. So now we are going that the much deeper into the machine learning. So we should be very careful, or we should be very aware of that. What are the topic we have discussed in the till the last week, like till the last, like till the fourth week. So now today we'll discuss the sigmoid, and then we'll be having binary cross entropy, and this is going to be used that's frequently in that deep in and all that we're going to use it out. So if anyone has, so please say. Otherwise, we'll solve some problem based on the last class. And then today we'll start the first classification, that the model that's called logistic regression. Okay, so hopefully there's no doubt till now. So I'll go and solve some problem that how it will work out and all. So they are saying like which of the following statements are true? Check all that and apply. So they're saying like if that the learning algorithm is going to be suffering from the high bias and only adding more training, just one that I'll be keeping camera switched off here and it will come here. Okay. So what will be there? So adding more training example may not improve the data significantly. Can anyone tell like what is the exactly like they're saying like if the learning algorithm is suffering from the high bias, it's something like it can be like it. They're not talking more about that so that the variance is not okay. So adding more training example may not improve the test error significantly. That is correct. Why? That the high bias, if the less variance, it's going to be high bias. What is that? Underfitting. If we talk about so adding more training, it's not going to help it out. So the first option can be correct. Second one is that a model with the that the more parameter is more prone to the overfitting typically has a higher variance. That's correct only. If we talk about we were having one like this curves was there. So this is the optimal parameter, and this we call underfitting zone, and this was the higher fitting zone, like not higher fitting, overfitting. Sorry for that. And overfitting zone that the variance was high, and in underfitting zone that the bias was high. Okay, so that first option is correct also. Second option is also correct. A model with the more parameter is more prone to the overfitting. That is correct only because it has a higher variance. So when debugging the learning algorithm, when we are going to debug the learning algorithm, so it is useful to plot a learning curve to understand if there is a high bias or the high variance problem. Yeah, it's correct only. Why? Because we have to like when so that the learning loss should be it should come like that the loss would be less. If we see that if we see any trend that's happening, so this is the loss. If we start like this, it will go like this, then it will become saturated like this. So learning curve like this, so that we have to draw the whether so there is a high bias or the high variance problem that we can see here and all. So that's also correct only. Increasing the degree of polynomial in curve fitting will increase the bias in the model. That is not directly that correct actually. So if you're going to increase the complexity, there may be a chance that the bias will get increased or maybe the variance will get, or obviously that the variance is going to increase compared to the bias and all. So it is not going to help in the case of what you can say that like it's going to cause the higher variance actually. So first, like A option is correct, B option is correct, and C option is correct. So I think hopefully it is clear. And then we have seventh question, like that till fifth we have seen around that the last class actually. So which gradient descent methods make parameter update for the training sample? Can anyone tell like which how many times we were having that the batch gradient, then that stochastic gradient, then the mini batch stochastic like in the batch what we were doing that the first so that the that the learn a batch and then a parameter will come. So if we are not going to do online modification or maybe update. We are not supposed to do in that. So this can't be. So in that stochastic like in that also we'll be able to make the change in every update. Like we can do it. So that the second one is actually a correct option. That the mini batch it will be like the both combination. So but they're saying like which methods make update for the each or every training sample. So that is the stochastic gradient descent. So in the batch gradient, uses the entire training data set to compute the gradient for the each parameter. So there is no that update we can't do for the each sample. Instead of that, we'll go for the per epoch. So it's going to pass through the all training data. It's not going to make for the every sample. The stochastic gradient descent is something update the parameter using the gradient descent compared for the single randomly selected example. So let's say we have there is some sort of examples or sample. So they're going to update for the each sample. So that's how it's going to work it out. So what about the mini batch gradient? A compromise between the batch and stochastic. By the name itself, It's going to update the parameter using the gradient computer. In that, it's a combination of the batch and stochastic one. Updating the parameter, it's called a gradient from a small random set mini batch of a data. So means parameter are updated after processing of each mini batch. It's a batch instead of sample. So that the third one can't be the correct option. First one can't be correct because it will go for the full training data. And for a statistic, like they will go for the each and every sample. So second is the correct option. So that the next question what we have is like consider a gradient descent rule for the rule with the momentum. Okay. Where the update for the weight iteration it's going to be given by like this. Like it's going to update like this and then it will make like this. So where like del JW, J is the cost function actually. So represent the gradient of the cost function with respect to the weight of at iteration T. Alpha is the learning rate. Beta is that the momentum parameter. What role does the term beta VT minus play update rule? Can anyone tell? So if we know about the momentum, like how it is going to work it out, like it's going to like update from the past update, like it's going to incorporating the formation, like it's going to converge. So they're going to increasing the convergence rate, and by updating information from the past update itself, instead of like we were having we were there X, and we were having some sort of model or black box Y came from this is the Y, then we have the so that the ground truth. And from there we calculate the j, and then it came like this. So this is something called like it's del j by w, but the momentum or its momentum something that will be going to like for each step we are going to that let's say x to y. I have to go just 1 minute. So the correct option can be like it's something accumulate information for the past and update, allowing the algorithm to remember from the previous direction itself. It's how the it learn. Add a fraction of the previous update to the current update, creating a momentum, then carry the optimization through the flat region from and small local minima. It's something like they're going to do in the each and every like uh, so that they're going to create a momentum through the flat region. So it's going to actually accelerate. Okay, one more question what we have. Same thing I think for the NAG. Okay, so we'll go with the this week content now that the fifth week will come across. So I will just give what's called like till now we have discussed about the linear and all in that, so that the logistic itself we were having in the fourth week itself, but we are going with that logistic one, and then we'll start with the back propagation applications and all, and then further we're going to start the CNN and all that will be going to next class and all. So we'll give some recap actually what's happened in the case of linear regression. If you remember, x is there, so that is a vector. And if we talk about like it will go to the y, that is our output, and some linear model will be there. That will be the weight and weight. Okay. Then we have the one ground truth. That will be y. From there, we'll calculate the j. J is nothing is a cost function or the error. or the cost function. Okay, just 1 minute. Sorry, like what happened? We were having that x, y. That is the output we were having, and then y is the ground truth, and some model was there linear. That is the function of x and w. From that we'll get the j. J is nothing is the cost function, and from that we're going to calculate the error. So j and delta j by w, and it's going to make some correction based upon that. So that's how that is the we have done for the linear regression. So this was the something called that's the linear regression. But now we are going to start with the logistic regression. That's the regression actually a classification algorithm. Can anyone tell like what is the classification algorithm? It's something. It will be. It can be it's a class, uh, either spam or not spam. Or in the case of linear regression, what we are doing with the time that the house market or house rent were there. So with the time how it was going, then the rent was increasing and all. But in the case of logistic regression, that we have to deal with the either the class, either it's a cat or dog or some other class will be there. That will be there. And in that case, so if we talk about like how it will go, so this will be x w and then summation, then it will come. So that will be the case of linear regression. And if the same thing, if you're going to introduce some sort of some like it's a x w, it will be linear combination. Then we'll do the summation. Now we are going to introduce the nonlinear activation activation function. That's will call g. Okay. then we'll get some sort of y that will be the predicted one. And that's how the things will be there. Like we'll say for this linear regression, we have the sigmoid function. Sigmoid function, we'll see how it will look like the sigmoid functions and all. That we'll see from and all. So this in this like it's a logistic regression. That's how it's going to work it out. So for any types of problem, that's all and all we are going to see what are the things that we have to take consideration. That I'll give the brief like how the things will go. So first thing for any problem in the machine learning, first thing we have to see that how we can characterize the like it's called representation, like it's number form. Why? Because a machines that will be taking in the class of like they're the numbers only. They can't take like a picture on also. Picture we have to convert into that's so that the matrix 64 by 64 matrix or 32 by 32 matrices, or maybe the cat is there, so we have to classify whether it's a cat will be the one or maybe the dog is the zero. So that's how we can characterize. Then after what is the feed forward model, which is like it's a like that's the what is the feed forward model. Then after, once we'll get so, but a feed-forward model is something like what is their linear function? Like it's something that's called linear combination. Then what is the non-linear activation? So somewhere it's a sigmoid function. Somewhere it will be that binary cross entropy, or maybe that the logarithmic some stuffs will be there and all. So once we get to know that what are the model that we have to give it out and all, then we'll be having what is the core function. What is the core function? Then after, how do we calculate the gradient? So this is the basic flow structures will be there. Then the last step will be the our most important. How can we get the like how can we going to minimize this error? So error calculation like gradient descent calculation. Okay. Once you calculate this one, so we'll go with that how to that optimize this error. Means like we have to minimize the error. Then we have to come up with that some things will be there. Then after we have to update the weight function. W will be W minus that learning rate into the error and all. So these are things. So these are things that are going to work it out and all. So now we are going to see what is the actually logistic regression actually. So if we go with that, like some bookish examples and also it's that the logistic regression is a supervised machine learning process. It's a in that the data should be labeled, used for the classification problem, unlike linear regression, which predict the continuous value. This so that is not going to do. Okay. So it is used for the binary classification, whether the output can be two possible categories, such as that the yes or no, true or false, either zero or one, either the cat, that's a cat and dog, anything can be done. For this LR will say logistic that the regression, it is used as sigmoid function to convert input into the probability value between the 0 to 1. So if we talk about like how it will look like, it's a feature 1, feature 2. Let's say this is the one feature, this is the one feature, and this is the one feature. So this, if any line is going to classify like this, so that line will say separating line or classifying line. Okay. So in the binary classification, In the binary classification, there will be a two class. Either it will be a zero, either it will be a one. So that's how we are going to label in through the mathematics. So zero can be no like zero can be like cat, it can be a dog, or it can be of anything. Like it's something that we have to classify in all and all. So in this case, it will be like this only. And actually, the input feature will be going to linear combination. Then this is going to be a sigmoid function. Sigmoid function. Then they will say either yes or no. It's a class 1 or class 0. So if you talk about what is the difference between the so that the linear regression and the logistic regression, it's going to predict the continuous value, predict the categorical classes, uses best fit line. It's a best fit line based upon the list square error. Here we are going to use sigmoid function and solve only regression, only classification symbol. So if you talk about what is the assumption for that, so in that independent observation should be there. Like one should not be going to that dependent on the other features and all. That the let's say x is the one feature, y is the one feature. So that x should be like both should be like that should be independent one. So one class will be like x will be there. Second will be the zero or anything. So that one line should be there. So they are going to classify the lines and all. Then uh, in this case, like we are going to mostly deal with the binary, but we'll discuss the multimodules also. That's the multinomials. Then there should be no outlier, and for LR, we need the some sort of large data. Large data means like we need the that's the more number of data set required. So if we talk about types of the logistic regression, it's a binomial. There'll be either class will be either 0 or 1. Then we'll be having the multinomial, more than two like unordered product, like it's a cat, dog, and sheep, or anything can be the three types. Then we'll be having the ordinal. Mostly this thing will not discuss in this like our course, but we'll go with the that's the multinomial, then the binomials and all. So that's how the things will work out. I'll tell you examples. Like let's say this is one thing. Then we'll be having the input. Then we'll be having the output wide. So 1, 2 till n will be there. Just 1 minute. Okay. So for that input will be like in terms of x vector, x1. Just 1 minute. Again, it got corrupted. I'll do one thing. Just 1 minute. I'll make the solution because it's auto updating. So it's making some problem. Change this one. Okay, fine. That will be having the x vector will be there. X1 in the one term, x2 second term, then we'll be having x1 second iteration. Just like similar way, it will go x1 in the m1, then x2 into m. So then their output will be either 0 or 1, either 0 or 1. Similarly, 0 or 1. Again, someone to join actually. Okay. So there are things that for the LR, it is going to work it out for that binomial regressions and all. And the sigmoid function is important for the logistic regression because they are going to convert the raw output of a model into a probability value of 0 to 1. Okay. If we try simple linear regression, 0 y is equal to w x1 w2 x2. So this will not going to give we will not have the data from 0 and 1. But the thing is that classification either it's going to yes or no. So there can't be of in between. So what they will do? So simple idea, we are going to do the squeeze the data to the 0 to 1. How we'll do it? So that's how that the sigmoid function will do. Sigmoid that so that the sigmoid function will do. So if you see around, so how it will go? So that the segment function is sigma of z is equal to 1 by 1 plus e to the power minus z. That's what the things. So this is actually a monotonic. Okay. So it's going to like it's a point 0.5. We'll make it here, and otherwise it's going to if it is going to sigma z tends toward the one, it's going to make an like it's something called infinity. If it's going to make toward zero, if it is going to minus negative, that's how the things will going to work it out. And it is always between the going to one, 0 to 1 only. So this is how the things will go. So that's how we can write it for the logistic that the regression, how we can manage this is sigma of z. And either you can write like sigma of w0 like this. So it's going to belong either 0 or either 1. Either 0 or either 1. It's going to make the sense like this. So that's how the things will go. So how it so it will go either 0 or either 1. If that the sigma z is going to that's the high value, it's going to make like 1. It should be like our value should be high. If it is going to minus infinity side, it means it's going to that the class 0. And sigma z always going to between the 0 to 1 itself because it's a normalizing function, we can say normalizing function, normalization. So before going into the other thing, like we'll so that we have other than the sigmoid, we have the binary cross in like a binary like entropy cot function. I'll take one page actually. So what we have binary Entropy cost function. So in the case of logistic regression, what we have sigma. And this is that, so that the W can be like it's a W0, W1, it's a vector form. It will come transpose. Similarly, it can go X. It will going to start from the bias. Bias will be like 1, X1, X2 till Xn will be there. So the thing is that we have to think like which function or which cost function should be that we have the good cost function. So it going to find out based upon the y, like it's a predicted one. So if we talk about the so that the least square method, okay, what will happen? Least square method. Oh, okay. So if we're going to use that the least square, so what will be there? J of least square will be half of y minus y square. So let's say if y is equal to 0, but y dash came 1. So what will happen? So j half of 0 minus 1 square, it came zero point 0.5. So what happened? So they are doing the misclassification, but the cost of error is too low. So it will not make much of sense. It will not going to propagate the things, so that so it's going to for the misclassification also, it's going to create like cost is not much, like let's say a that the patient is there, and if it is zero point 0.5 and there is no cancer was there, or maybe that the actual truth was no cancer, but what happened, it came around zero point 0.5, and it went automatically that the cancer is there. So what happened, like it's going to be like it's giving the very low cost value. It's going to happen, but it's been so that's why for the misclassification, so the cost for the mixed classification is very low as compared to the that the cross entropy and all that will like tell you. So to deal with that, that the, we have BCE binary cross entropy, that the binary cross entropy cost function. In that also J is equal to minus Y, it's the ground truth, ln of predicted one plus 1 minus Y ln 1 minus predicted one. So this is how the things will say. This will call binary cross entropy. And if you talk about the what is the properties at all, J is equal to 0 if Y is equal to Y dash. And J should be high. Misclassification. For the J should be very high for the misclassifications and all. Let's say I'll tell the things will be like if we take Y is equal to 0 and then the Y predicted also 0. So 0 log 0, it's going to be like 0 only. And 1 minus 0 and ln 1 minus 0. So it will become ln 0. So what have happened? So ln 1 will become the infinity. Infinity means that the cost function it become too much. So that's why we have to be think about like when the cost function is too high, so means they are giving the better cost function is good for that particular classification. If we use the that the list square, it will not give much better results and all. Even if you take let's take if you are taking the example, one is that y was 0 and predicted one was 1. So if you calculate the so j will become infinity. Why ln 1 will become the infinity and all. Or either if you're going to reverse with that also, so means that the cost function became too high. So it means that like they so the means they so they are warning it like it's the cost function is too high. It's not doing proper classifications and all. So that will be able to change the like something called model. So I think that if we came across the so these gates will be there in the electrical branch and all electrical engineering, or we can say in the electronics also, EC branch also, OR gate. Can anyone tell like how does the OR gate will look like? For that input will be x y x like it's a vector one. So either it can be 0 0 and this is the y. Fine. So what happened? It will give 0 0 1 or miss either 0 either 1 it will give the like majority one like it's a 1 1 0 it will give again 1 1 1 it will give 1 again. So it's actually a what is there binary class. Binary class problem. How come it going to look like? How come we have x0 it will that will say bias, then we have the x1, then we have the x2. We are going to summation and then we are going to apply the sigmoid. It's a s function. Then we'll get the y. So they're going to classify either 0, either 1. Either 0, either 1. So that will say sigmoid. No, this is a summation actually. Sorry. and this is the sigmoid. Okay, so that's how the things will go it out. Like let's say Z. So if you're going to put like this, like it's a bias x1, x2, and we'll be having summation that will tell it's a called a linear function. Then we'll be having a sigmoid. Then we'll get the value of y bar. So this will say sigmoid, and z we know that what is that? Fine. So the thing is that what I have to do, like what weight it's going to, what should be the weight value? They should give the OR gate. What should be the weight value? They should give the OR gate actually. So what can be should be there? Like it's something. Let's say it's a 001. So it's a y. So y bar should be 001. So it should be less than of zero point 0.5. Means our segment function should be less than of zero point 0.5. Means it's a negative one. And for that to come closer, it should be greater than zero point 0.5. Positive, positive, positive. So how can we do it? Like if you're going to put that our z value should be should be something like we can get like y. Okay, y will get sigma of z. So it should come like greater than or negative than. So if we take the z w0 is equal to -1, w2 2, w2 2. That let's keep this value -1, -1, w1 2 into 0 plus 2 into 0. So it came -1. It means negative. So it came the value like this. Then if you're going to keep z is equal to -1, 2 into 0 plus 2 into 1. So what happened? It's going to cut it out. 2 minus 1, 1. It came the positive value. So means for that particular gate, our weight should be -1, 2 or 2. So similarly, so that you can check for the AND gate also, XOR gate also, and that the NAND gate also. I'll give it just brief of how the AND gate will look like, XOR gate will look like, NAND gate will look like. So how the AND gate will look like? Anyone have the idea? So we have the x1, x2, and then y. Oh. 0, 0, 0, 0, 1 will give 0 only. 1, 0 will give 0 only. And then 1, 1 will give 1, 1. So it's again a binary class problem. What about the NAND gate? How the things will look like? NAND gate. AND gate is there, not of AND. 0, 0, 0. AND gate is there, not of AND. So it will become the 1. 0, 1, 1. And 1, 0, 0. Like it will become the 1. 1, 1 will become 0. So this is NAND gate. Again, the binary class problem. Then what we have XOR gate is there. XOR gate, what was that? 0, 0. I'll not go much of detail like how to get the that so that the weight value and all. Okay. So OR gate 0, 0, 0, but it will going to turn out with the XOR gate like 0, 0, 1, it will become 1. 1, 0, it will become 1. 1, 1, it will become the 0. When the both are same, like it will become the pattern only. So they're not going to separate properly. It's again the what you can say. What you can say, we'll be having the binary class problem itself. So what is that? Like sometimes what will happen that a feature, let's say I'm saying like this one things came out like this. When 0, 0, 0, 0 came, then 1, 0 here, 1, 0 like it came for this case I'm saying 1, but 1, 1 again came like here. What happened? So they're not going to separate properly. One line we can create. If that a line can't create, a line can create. So what we have to do? We have to create a plane, or maybe that some sort of some either kernel or the nonlinear plane should be introduced. Okay. So if we talk about that, how the gradient of the log likelihood function will look like. So we know that like J, what was that? Or maybe Z. J was the sigma of Z, and Z1 was like this one, and sigmoid function what we were having 1 by e to the power minus z, e to the power z. Sorry, what was that? This is the function was there. What we have to do? We have to do like and then it will come like this. Then, but either it can go either you can add the kernel. This parameter will see for the SVM, that is the RVF, reduce function kernel, first order kernel, second order kernels and all. Or maybe you can add the extra layer. Add the extra layer. So that's how we can do it out. Okay. One more is this differentiation, like differentiating the sigmoid. How will it look like? Sigma z, we know that 1 by 1 plus e to power minus z. So if we do sigma z, it's going to 1 by 1 plus e to the power z, whole square, like it's a whole square, and summation of like you are doing with the differentiation of, like it's a chain rule. So what it will come? It will come like 1 by 1 plus e minus z whole square into e to the power minus z. Like it's minus 1, it will go. So it will be like this only. So now what we can do? We can get 1 by minus z e to the power z 1 e to the power z. If you're going to simplify this, so this one, so we'll get differentiation sigma dash z is equal to sigma z into 1 minus sigma z. So this is the one thing we'll get. So now the things will again the one will be there. What will be the gradient of the things? Like that the gradient descent of sigmoid. I'll take one page actually. I'll not go much of detailing of this, like how the things will look like. I'll be giving like how the things will go. Like one will be the bias, then x1, x2 till xn, and this is the summation. It came from here, weight 0. So this is summation. Then we'll be having a sigmoid. Then we'll be having a y bar, like it's a prediction. Then we'll be going to get from the, what I can say, j. It's a called. So now from here, gradient descent. If you're going to simplify from the x vector, it came to z. That will apply the chain rule. Just 1 minute. Okay, fine. What we were having? We were having so for this we can write as a simplified way. How come? And from here we'll get the j, and to update here it will going to gradient descent. How it will look like? So we can write like this. It's a summation. We'll get the y bar from j. So this is z. This is g. So what will be the here is the w. So delta j by w we can write how? Delta j by chain rule. Just apply the chain rule. So chain rule apply, and then we can get it out like what is the j value. So if you're going to simplify that one, so what will be there? So our j binary cross entropy is something what we have like simplified way minus of y ln. So yi ln yi plus 1 minus y ln 1 minus I hat. Okay. So can we solve one example, or I will be if you're going to simplify that way, so it will come like this. I'll tell you what will be the final expression. Then we'll solve some problem also. So let's say for a m like that x value. So if you're going to keep like j is equal to m, so delta j by delta w 1 will look like how? Delta ji will look like delta ji upon delta for the particular x value. So the final answer, what we will get? Delta j by delta w weight is equal to 1 by m. If it is a number of sample is the m, so 1 by m will get. So it will look like this. yi of xi. So if you see around, it's going to look like how y minus y into the whole square. Well, things will be there here. It's going to same as the list square functions and all. So for the logistic regression, the loss function is not going to convex. It's a paraboloid. If you see like this, it's going to look like this. So that is the so for a logistic regression. So there will not a single unique separating line will be there. So that the solution will be not the general. It for a classification they can if we take a different weight, so we'll get the different separating line. Okay, so means it's not going to give the like a global optimum value. Like a general will not give the same optimum value and all. So now the things that we have done, so now we'll go with the multinomial classification. Multinomial classification, till now what we have discussed, we have discussed what is sigmoid function, and what is the gradient of the sigmoid functions and all that we have seen around. Now, so if we see around, so this is how the things will look like. Sigmoid, like no, it's that the gradient yi minus p of, like it's a predicted one, like y hat actually. Then xij value. It, like when we'll solve the problem, that we'll see around. Then now, so now things what we have to target three variables instead of binary, like a 0 or 1. Now what we have, now what we have, it's a three, or it's going to be that's the more possible type. It's not order. Maybe that this is A, this is B, this is C. So to deal with that, to deal with that, we are going to introduce the one hot factor. One hot like that. The one hot factor is something that we are going to keep like. I'll just 1 minute. One hot factor, like that. The one hot factor is actually how it will look like. Let's say in a box, or maybe something like the picture is there. Either the cat, either the dog is there. So how they're going to put in the vectorized form. If it is cat, we have mentioned one, so it's going to one. This will be zero. So this is going to be for the cat. For the dog, it will be the 0 to 1. So let's say if I have the cat, dog, horse. So that the how it will look like vector form. So that's how it will look like the vector form. 1, 0, 0. For the dog, 0, 1, 0. For the horse, 0, 0, 1. Okay. So means, so they're going to like and if we get the corresponding y bar, like y hat, it will going to look like this. Y, or I'll do like this. Y1 hat, Y2 hat, Y3 hat, to the transpose. So this is how things will look like. So now to deal with that, for that like binary classification, we were having what binary cross entropy, or maybe the sigmoid was there. Now what we have to deal with the softmax function. What is the softmax function? It's going like it's a softmax function is going to use instead of sigmoid. Sigmoid, like how come it's going to, like let's say softmax is z, is actually a normalization problem will be there. E to the power z, just 1 minute. So e to the power z, just 1 minute, into summation of j is equal to 1 to k e to the power z j. It's a optimization function. Let's say we had so that we are having x, an image is there, or maybe an image was there. We have done 60 by 60 as there, so that the input will be 3600 by 1. You have to get the z. WWX, and it will be going should look like because I'll be going with the three class problem. So what they will do? Y is equal to soft max Z1, Z2, Z3. Okay. So softmax of Z1, Z2, Z3. So it will going to look like e to the power Z1, e to the power Z2, e to the power Z3, 1 by D. And D, it will look like e to the power Z1 plus Z2, Z3. Okay. So for this, okay, that before that I'll be going to for binary logic that the regression. For the binary one, K will be 2. So that the K will be 2. It will be either, and then the non-linearity, it's a binary cross entropy. It will be J is equal to minus of y ln y hat plus 1 minus y ln 1 minus y hat. One thing. So for the multinomial, K is going to be greater than 2. For this, we're going to use the one hot vector. Then after what will be that the non-linearity will be what will be there? Softmax. And if we talk about the what will J, it's again will not go with the what you can say K is equal to 1 to K YK ln of YK like hat. The things will look like this. So it's again a combination of the so that the what will say like that the linearity and the non-linearity. So I think that the comparison between that so that the linear regression and then the logistic regression we have seen around. So now we will see the schematic of the multinomial regression. A schematic of the multinomial regression, how it will look like. This, this. For example, oh, sorry. So for example, if we see around, we have the one bias function x1, x2. How much is there? X3. Let's say I'm going with the 3. So for that, what will be having? yi 1. Like let's say y1, y2, y3. It should going to from here, from here, from here, from here. It will go. Then from here also it will come here. From here also it will go there. What we are having around bias, or we'll say 1, x1, x2, x3. From each get we'll get y hat 1, y hat 2, y hat 3. From here it will come, it will go to here also. 1, 2. From each will go. Similarly, it will go for the all cases. So I'll write the soft max 1. It will come from here, where from the 0 1, weight of 0 plus 1, 1, x1, 1, 2, x2, and not x2, like 2, 1, x3. So then y2 will look like this. 3, 2, 1, 2, 3, 3, 2, x3, and y3 will look like this. Okay. So the things will be like so total we are having the weight how much? 1, 2, 3, 4. For each case, 12 weights will be there. So what we have to do, we have to guess the weights, and then accordingly we have to play around the weights, and then we'll be getting the y value. Then we have to do the softmax function. So now we'll come for the our neural that the network. How things will look like in the neural that network. They're going to mimic the complex function of the human brain. So let's say something that so any activity that happen. So through the dendrites, like it will go to the axon, and then it will go to the nucleus, and then they're going to send the signal to the brain. So that's how the things will go. That's the input, and this is the things will work out like it's the one will be the linear function, second will be the activation function, then the output will come into the factor. So like it's a again for this also we'll be having that threshold value. Let's say if some person is sleeping, so some people will going to just okay, so they will push okay, just wake up, but not it not so they're not going to wake it up. What will happen? We have to increase the intensity to either hitting or something that will do. So it's a threshold value. If it go beyond of the threshold value, so what will happen? So that brain will going to activate. So that's the activation function. So what we are having, it's a one type of function will be there rectified that so that the linear that the what you can say unit activation will be there. So in that also, so it's a similar one. It's a linear function, but instead of that we have sigmoid or the non feature that we have the activation function, then we'll get the output. So it will come from the bias. It will be always there. Like it's something y hat the g of g is the activation function. W into x, like from the x it came plus b. So one will be from the x to y, x to y. So that will say feed forward model. Okay. So if it is like this will be there, so that will say that the feed forward model. So let's say we are having x1, x2, x3, then we'll be having the number of neurons will be there. It's going to connect from the all this point from there. Then again, one more that the like we have the neurons will be there, and we'll get some output. It can be of anything. So first one will be the input layer. That will be the output layer. So this will be the hidden layer one. This will be the hidden layer two. So that the input layer and then output layer, that is not necessary. That should be same. Input layer and output layer, it will be not necessary. That is going to be same. So it's going to make like neuron will be like it's if we have the more than one that the hidden layer, so that will say deep neural network. Okay. So from this all will go to the all hidden layer, that's called neuron. So solving this, so if we are going to solve this problem, if we are going to solve this problem with that, what we can say, that's called feed forward. What will happen? What will happen? Let's say I'm going to, we are having X. From there, we have the activation. Again, the activation. Okay. And then we will be going to get Y. From there, we'll get the J. So it's a cost function. So in the back propagation, what will be the things? They are going to redistribute the error. Okay, this thing we'll discuss later. If we'll go for the simple method. So first what we have to do? We have to guess the weight. Then we have to update it. Okay. Then we are going to make the, so that method we say finite difference method. But what will happen? It's going to be very expensive because they're going to going through the all the weights from that from the first input W1, W2, W3. Then it will go from the second one, then third one. Then from the here things will come. Then it will go from here, from all. So what will happen? It will become the expensive. Is it? It's going to be simple only, but it's become the very expensive. So to deal with that, what can we do? We'll find out the J. We'll find out the J. Then we are going to redistribute. It's a chain rule that we have done in the case of that the software function or maybe segment also, that we have done the gradient rule, gradient descent. So I'll tell you the one that the last example, like I'll that so that how the things will look like the structure. I'll tell you, and then we'll solve some problem based on that. So let's say we have the x. Okay, it's a vector, weight one. Then we'll get the activation two. Then let's say this is the one activation. We get weight two. We came across. Just 1 minute. So what we have x, this is the input vector. Let's say for corresponding activation this much, and we are having will be giving the weight 1, like for the so that is the actually a vector actually will get a2 like this. Sorry for that. We'll get activation 3. Then from that we'll be getting final output. Then we'll get the j value, and from the j, from the j we're going to get the. So if we simplify the similar way what we have done for that the logistic regression, let's say x, it's a w1 and z2, just to 1 minute. G, activation of 2, it's a w2 will get z3, activation of 3, then w of 3, a4. From that we'll get the j value. If we talk about the a1, it's a activation of 1, it's a bias. X, z2, weight of 1, activation function of 1, z3, it's a weight of 1, activation function of 1, z3, activation function of 3, activation function of second, like 2. Yeah, just 1 minute, we'll see. Then the Z4. Z4 will be, it's a Z4. A3, W3. Okay. So now the things will be, what will be the A2? A2 will be G and Z2. Okay. What will be the A3? G of Z3. A4. G of Z4. So the question will be, what will be the delta J upon delta W1, delta J by delta W2, and delta J by delta W3. So we have to get, so like we have to get it. So I'll be giving the final expression for that, what it will look like. The final expression will look like, so final expression will look like delta J by, for anyone, like it's a delta of L1 into activation of L1. So how the things will come it out, like I'll be telling like from the chain rule actually. If we go around delta J by delta 3, because we were having around here W W3 corresponding to this. So how it will look like, delta J by delta J by A4 into A4 by Z4 into Z4 by W3. So this is the things that how it will look like. This is going to be a what? Delta J by so delta A4, delta J by A4 by delta Z4. It's what will say, delta J by Z4. It's nothing but a gradient in terms of y minus y, and this is going to be a A3. Okay, so it's making that something like delta J by delta Z4 is actually error of that term. So similarly, it will, can go delta J by delta Z L will become delta by L. So that's why that if we talk about the general what I can say expression, so delta J by delta W L will become error for that corresponding L plus 1 into A of L. So now we'll solve some problem based upon that. Okay. Yeah. Okay, so we have the first question is there. The machine learning model is trained to predict the category of the various finance related objective. First one is the investment. saving retirement budget. When the preparing the data that the one hot encoding is applied, now they are saying finance related objective as classified as a retirement. Like that the our final output retirement is one and others are 0, 0, 0. So they are saying what will be the one hot vector. So we have to see now for the retirement, it is one. Other should be zero. So first option is correct. So this can't be correct because the retirement our output like classified it came word retirement. So that can't be zero. This can't be zero, but this also can't be correct. Okay. Then what we have second question. What we have second question they are saying consider a neural that the network that classified the data into the three category A, B, C. We have neural that the network A, B, C. So for the category A, they've given five. Category B, they have given two. Category C, so they have given three. So they are saying calculate the soft max probability for the each category. You know that what is the soft max? E to the power z I upon summation of e to the power z j. Like whatever things are there. Like for the corresponding the things with that. That's the normalization. So we know that ZA, it's a ZA, it's a ZB, it's a ZC. So what we'll do? We are going to find out the e to the power ZA. So e to the power 5 will look like how much? 148.4132. E to the power ZB, it's going to look like e to the power 2. It came 7.3891. E to the power ZC, it came e to the power 3, 20.855. So now we'll get the summation of all the ZI. So 148 4132 plus 7.3891 plus 20.85. So it will be going to becomes 178. I have the calculation, so I'm just giving the values. So now they find the soft max of ZA. So ZA by summation of all the Z. So ZA, what is there? 148 upon 178.8875. So it will come how much? 0.84. And the soft max ZB. It's a ZB by summation of e to the power Z. So ZB, how much is there? 7.389. 3891. 7.3891 upon 178.8875. So it will be giving how much? 0.042. So option A is correct. Similarly, soft max ZC, ZC by e to the summation of e to the power Z. So what is there? It will come this value. So second question also clear. Now the thing is which of the following are not true about the sigmoid function? Can anyone tell? It is going to value in the range of 0 to 1. That's correct. That we told. And this function is actually a what? Monotonic. It's a correct. It's not the, it is a non-linear. So this is not correct. Segment function is differentiable at every point. That's correct. So option C is the correct answer. So now the question what we have, they are saying to find out the cross entropy. Binary cross entropy, they have given the formula. Let's say it's a J function they have given. And the number of sample of how much we have, it's a 5. So they are trying to find out the what is the binary cross entropy this for this function. Can anyone tell or can anyone find out? So if I'll go with this for sample one, it is actually what? Pi or till now I was saying y hat. For sample one, I'll go. What will look like? They have given the y1 as 1 and pi is actually zero point 0.9. So BCE will look like how much? If you go with that formula, that it will going to look like how much? Zero point 0.9 minus plus 1 minus 1 ln of 1 minus 0.09. So if you calculate this all, it came 0.054. Similarly, if you go with the second sample is actually y2 is equal to 0, pi2 it's a zero point 0.2. So BCE, not BCE actually, sorry, not the BCE. It will be PI, P1, P1, and it's going to be a P2. So zero point 0.2 minus 1 into 1, 1 illa, 0, ln of zero point 0.2 minus 1.00 ln of 1.2. So it will come how much? 0.2233. Similarly, if you calculate the P3, we'll get again 0.2233. P4 will get 0.0513. P5 will get 0.015. So that the BC will going to look like 1 by n minus 1 by n is the 5 summation of all 0.1054 plus 0.00231. If we calculate this one, so this value will come 0.1416. Accurate option. Now the second question what we have, they are saying to find out the sigmoid loss function. Consider logistic with the sigmoid function with that and initial weight. So what is the BCE after the first iteration? Can anyone tell like how it will go? So they are saying to calculate the initial weight as a 000. Okay. So it's corresponding to, okay. So it will go into P y is equal to 1 at x given sigmoid of 0 x1 x2. Okay. So 1 by x2. And if we keep this all value, how much it came? 1 by e to the power 0. It will come 1. 1 by 2, it came zero point 0.5. It came how much? Zero point 0.5. So P for all the input, P for all the input came how much? Zero point 0.5. So now for the y is equal to 1, for the y is equal to 1, what is the P? It's a zero point 0.5 minus 1 into ln 0.5 plus 1 minus 0.5 ln 1 minus 0.5. So if you're going to get this value 0.0693. Similarly, if you do for the all, then the value will be same. You can try at home P2, P3, P4, and then P5. So we'll be having same 0.693. If we calculate for the all, we'll get the 0.693 because that the BCE will be again 1 by n summation of all the PI. So all the things 0.693 into like times of the 5 times of the 0.693. So 5 by 5 will go and then we can get the value. One more question what we have is to find out the delta J, delta W. So alpha they have given 1. Initial rate they have given 0.000. Okay. So delta J, delta W is actually delta N summation of Pi minus Yi. Pi means it's the predicted one into Xij. Okay. For bias term, it's a 1 by 5, 0.5 minus 1, 0.5 minus 1 into 1. Then after it's a 1, then it's a 0. 0.5 minus 0 into 1. Then after, for similarly, we'll go with the uh, zero point 0.5 0 into 1. So this will get minus of 0.1. 4, it will become 1 by 5. 0.5 minus 1 into 0.3. 0.1. Similarly, if we'll go with the 0.3, 0.5 and all, I'll do it. Point 0.9. Okay. So for that we have the mine again 0.1. So this is second option will be the correct option will be there. So that's all for today. And if you have any doubt, okay, this last question I'll solve, and this will again solve in the like that's the next class only. Okay, fine. Any doubt is there? I think the last question can be maybe doubtful, so that I'll explain again. So if you have anything to ask, please ask. And sorry for the glitch and all. Like I'll be changing my laptop. Maybe I'll take some other laptop or I'll sit in the lab and I'll do with the system itself because there is some much of issue with the PPT and all how it's coming. I don't know because maybe that I'm using the OneDrive. OneDrive it's updating by their own. I don't know if exactly. I have to that to figure out. Okay, shall we wind up? Okay, fine. That the last part I will explain in the that's the first hour of that. So that's the next week. Yeah, point five. How it came, I'll tell you. Point five. How it came. Like if you see around for the zero weight, for the zero weight, we know that we know that if you're going to take just 1 minute. Uh, For all they've given 0, 1, that 0, 0, 0, then we know that that the probability will be sigma of z. Z what we have? W0 plus W1, W1 x1, W2 x2. And we know the formula of that the sigmoid 1 by 1 plus e to the power that's the minus z. If we keep the all value 0, so e to the power 0, e to the power 0 will become 1 by 2. Like e to the power 0 will become 1. So 1 by 1 plus 1 will become 2. So it will become the point 0.5. So that's how it came the point 0.5 for the case of the weight 0, 0, 0. And in the second iteration, whatever the weight will come here, so that will become the second weight. So that will going to keep in that that's the W0, W1, W2. And so there might be a doubt like how it came the for delta J by W2 is the 1, then delta J by W1, it came point 0.1, point 0.3, point 0.5, 5.7 and all. So that we will discuss like how it came and all because there's one more form that the formula will be there. Okay. It's fine, now. Shall we wind up? Okay, then thank you. Yeah, sure. I'll share the PPT also, and even that whatever the question I'll send, that I'll send the content also, like how the answer will look like in that drive. Sorry, like I didn't upload as such till fourth week. So by tomorrow I'll upload all the from the first week to fifth week, all the questions that what I have solved in that session that I'll upload in to there also. Okay then. Okay, thank you.